about Haskell in the mission control domain and how we use it there. So just short about me. I'm working for Siemens Space since 1998. We have been carved out now, the whole software department of Siemens has been carved out into Siemens Convergence Creators, the CVC. And currently I'm the project manager and technical lead for the maintenance and evolution of the Gecko's mission control system for DLR. It's a system which is based on ESA's SCOS 2000 mission control system. And it's used for the current missions. We have actually TerraSci X, Tandem X, which are mostly scientific missions. We have TED-1, it's a test mission, and SATCOM BW, it's a military communication satellite. These are the missions which are actually flying. We have the system for pass we have ready, and we are waiting for the launch. And for EDRSA and HAC-1, we are currently heavily modifying the system and are on the finishing phase. So that's just short what the company does in the space sector. I just skip it because of time reasons. So this is an impression of the control room K1 at DLR. So that's the main working area. So what you see here on the screens is basically two systems. It's the mission control system and a system called SATMOM. The mission control system is responsible for getting data to the satellite, so we call it telecommands, and for receiving data from the satellite, it's the telemetry. And then it does archive them, process a lot of checks and so on. And the SATMOM is connected to the SCOS and gets the data, and it does visualize them because it has much prettier displays. And the new version of SATMOM is developed by a company called Heavens Above, and it's written in Scala. So maybe next year, they are not here today, but maybe next year we'll hear something from them. Okay, and here you have on the right the big screen. This is the central application. This is the so-called manual stack. Each line you see here is a command which goes to the spacecraft. Then you have, this is the commanding console. From here the commands are sent. This is a supervision console for the mission control system itself. Here is for payloads, or cameras, instruments, and whatever. This is for the attitude and orbital control management system, so for tracking if the spacecraft is on the right track, which is not always that easy, but maybe Björn will tell something about it. So this is just another impression that's of a picture of Rosetta and me. So maybe you've heard of Rosetta. It's a space probe which has now reached the comet Churyumov-Gerasimenko, and they put the lander on it in November. And I'm just looking onto the underside inside the spacecraft. And that's because if you work in space, it's either very boring or very stressful. And if you have to get such a baby up, and it's now a few million kilometers away, and it's performing quite well, it's a little bit of a reward for this work. Okay, so but back to Haskell. So what we do. We mostly work with the mission control system from ESA, and it's really a big mess. It was developed from more than 20 companies with different styles, different knowledges. It started with C in the end of the 80s, was then converted into pre-standard C++, and yet stopped. So this is basically what we have. You have all sorts of problems that you can get. Uninitialized memory, memory leaks, no use of modern, more safe idioms. You have low-level pointer arithmetic copied to 100 places, and if you update it and you miss one place, you get burned in hell. Off-by-one errors, undefined behaviors, this static initialization or a fiasco, name it. Threading problems, race conditions. The biggest joke, SCOS 2000's own Mutex class is not thread safe. We have no clean thread termination, we have very low modularization, we have shared data scattered across 770,000 lines of code. You have pre-major optimization problems, and this was not designed for multicores, so that's all the challenges we have today. And it can even get worse because we can't use tools of Valgrind or Purify. They don't work in most places. And we also can't use GDB only. We can use it only occasionally because we have timeouts and deadlines. So if you hit the breakpoint, you miss the deadlines. So you can imagine what this means. It means maintenance nightmares. And I speak of real nightmares. So if DLR calls you because they're repositioning two spacecrafts flying information, and suddenly the system was working for 7 years without a problem, and suddenly the commanding chain was locked and they couldn't get commands up, and they lost also 2 ground station contacts. So it's a very bad situation, because if the spacecrafts collide, the mission is over. And the ground station contacts also, they have to rent the ground station, so this is very expensive. So this is what really happened to us. And if you have ever had the situation that you sleep at night in a dream and walk through data structures in memory, and put some objects into vectors or standard maps. Yeah, and there comes a thread in, it gets the data before you. And then in the morning, you wake up, and because the alarm clock rings, and you say, oh no, I don't push that button with my finger, I just cast a pointer to it. Then you know what I'm talking about. Yeah? That's sort of maintenance nightmares. So, while banging my head against the keyboard and asking the maintainer question, why me? Yeah? I mean, I know that because unfortunately I'm quite good at this stuff. So, I came across this famous paper. I think many of the Haskellers know it. If not, you can look it up on the internet. And this was about implementing a prototype in different programming languages for these points here. Yeah? And I said, oh, that's exactly what I need. Yeah? So I looked at it. And the winner was obviously Haskell with some absurd low line count, which got the other programming languages quite impolite. But yes, then I had one semester of Haskell on the university, so I thought, okay, I have to look at it again. So that's what we did. First, the goal was to gain some Haskell knowledge with some small tools, so data conversion, processing, the usual stuff. And then how to check the appropriateness, if we can use it. So we can't simply take a component of the mission control system and replace it if we don't know that will work. So we searched for something that is external to the mission control system, but with nearly the same requirements. Yeah? And that's what we did. And it's quite a small application, but for us it's really useful. So we needed a simulation and validation tool for the implemented new features of the mission control system so that we can test it in a closed loop. So you connect the mission control system to it and then execute a lot of tests. So it needs to simulate parts of the network control tracking and routing system, the ground stations, and of course parts of the spacecraft itself. It's based on the ESA packet utilization standard, which is a derived version of the CCSDS standard. And we had nearly no budget and not much time, so fairly common software project. So that's it. So it looks a little bit different than normal desktop applications. Yeah? So you have on the right side, we have connection indicators because we need to have a visual indication as soon as the connections from the mission control system drop. Then you have a big the mission name, yeah, because we have various missions that you need to see at one site which mission you are in. Then this is just basic logging, so you have basic logging on the top, in the middle, each telemetry packet that it sends, and in the ground, each admin message it sends to the mission control system. So this is the commanding page. So you see here, on the top there is the internal state of the receiving end for the telecommand protocol machine, and you can also manipulate it and then see how the mission control system reacts to it. And then on the bottom you see this is for the TC authentication. So most TCs, if they're sent up, are either encrypted or have to be authenticated. So you have keys, counters, whatever you need for this. It's ESA standard authentication. This is a bit more interesting. This is the telemetry simulation. On the top you have some settings, and in the middle you have, if you look here, this is a Haskell data structure. Yeah? So what we did is, if you derive a Haskell data structure with read and show instances, you get the deserialization from and to string for free. And so you can type in here arbitrary telemetry and send it to the control system. This was the one thing. The second is we have the possibility to compile GHC in, and then you can use full Haskell to create telemetry however you like. We don't use the feature often, but we have the possibility to do it. And also we can load here a lot of different formats of recorded telemetry and replay them. It's also very, very often used in testing. I once requested a telemetry for a special satellite that I got from Astur Toulouse. I got a Microsoft Word file with some obscure text format in French. So I converted it to a text file, wrote the parsec parser, and now Paragon can also send French telemetry. So that's just a simulation of the onboard queue of the satellite. So you get commands and they have an execution time associated when they should get executed on the spacecraft. And you can manipulate it, you can request dumps for the mission control system and whatever. This is the same for the onboard software maintenance. So this is for testing software uploads. You can dump memory, you can copy memory on board, you can request checksums and so on. This is just for performance testing. So it measures how many commands and packets per second we get through the mission control system. It was used for tuning performance. We have some high bandwidth missions, and we tested if we can reach the required speed. Yeah, that's also there's just some admin messages to send, and here we have the simulation time. So the spacecraft, of course, has its own onboard clock, and here you can set properties, also the clock drift and whatever, and then you can see if the mission control system can correlate the times, and yeah. And this is also a telemetry generator, but this one loads the satellite database. So you get a list of packets, click on it, you get a list of parameters, fill it out, send. And on the right side you have some data generators for special telemetry. They are mission specific and are only enabled for specific missions. So you have, for example, the LCT that is for the laser communication terminal for ADRSA. And the thing about this page is, without the data generators, so implementation of the GUI, of the loading of the database, the model and the business logic, it was 3 days. We had this similar tool to develop in C++, not the same, but similar complexity, and it took us 12 days. So we had about the productivity was 4 times about, so this was quite an interesting experience. Okay, it worked well, so we did another tool, which is a protocol bridge. So the spacecraft simulators and the mission control system speak different protocols. So we implemented the protocol bridge in between, so it speaks to both. It was based on the Paragon TT, therefore it was a quick implementation, and this is what it looks like, so it's quite similar. You have some logging, you have some settings, you can also record telemetry, and here you have a quick look what's currently flowing through it. The thing was, we had a bug in one of the spacecraft simulators. It did put 2 telemetry frames into one protocol data unit, and DLR at that time for testing used 2 pieces of ground station software, and they couldn't handle that and cut the connection, so they couldn't continue testing. And there was a meeting, and we discussed this issue, and they said, okay, they will fix this bug in the spacecraft simulator. This will take 2 to 3 months, maybe. Yeah. Then they looked at the people for the ground station software and said, yeah, okay, but we have to ramp up the development stuff of this, yeah, so a few days to 2 weeks. Yeah. Then they looked at me and said, can we do something? And I said, yeah, give me half an hour. I was a bit optimistic, it took me 1 hour, but then I had this thing up and running, yeah, the telemetry was flowing through, and they could continue testing. So that's what customers like. Okay, so this is a comparison of Paragon TT with some 2 tools, the TC tool and the TMPI for telecommands and telemetry. They are delivered with newer versions of SCOS, they are in C++, but they don't work seamlessly together. So you can't really drive so closed loop tests. Yeah? And you see we have here a lot of features and here a lot of missing things, yeah? Also for the telemetry side, and for these are complicated things. So they are completely missing. And so here we have actually a line count, so the current application is 23,500 lines in Haskell. For the C++ tools it's quite difficult to specify an exact line count because it uses libraries from SCOS. So the min bound is actually only the GUI and the business logic of the tools itself, and it's already higher than the Haskell. And the maximum is if you include also the SCOS libraries it uses. So you have 94,700 lines. Yeah. Development time for Paragon was approximately 7 months. Yeah. I can't say it for sure because of my lazy evaluation of time and the iterative call by need nature from DLR, they call and need a feature. So yeah, for the C++ tools, I can't say it exactly, but I talked with a company that developed a very similar thing. They had 1.5 to 2 years. Also for the bug count, I don't have access to the ESA database for the bug count, so I can't really say, but there are still several seg faults inside. And if you remember what I said about the code quality, and you look at 700,000 lines of code, you should already get some shivers down your spine. So we had 27 bugs in Paragon, and 1 seg fault because the silly programmer didn't know how to use GTK, yeah, me in this case. Yeah. So what do we find, what were the advantages? With 1.5 to 4 times the productivity compared to C++. And that's quite good. It's not only important to sell it to the management, but it's also important for us. We get a nice project in, and we say, yeah, happy we do this, yeah? and then the management says, no, we are in Austria, you are too expensive. Yeah? And then the people in Hungary, in Romania, and in Czech Republic get the job, yeah? Because they cost only half of me. So, but with this we can still compete, until they don't Haskell, of course. So we have less bugs due to strong type system. Of course, it's quite a Haskell slogan, and that's a personal experience for me. I think more about the problem domain and less about how to code it. Yeah, in C++ you have to worry a lot about a lot of things, and because of the mathematical nature of Haskell, you think a little more about the problem. And also, it's very easy to change the architecture. So if you want to have different threads, different threading architecture, you simply try it out. If you do the same in C++, you're going to know what to do the next week. Yeah, so that was really fun to do. And concurrent programming is much easier due to SDM, but still hard to get right. Okay, the async library rocks. Yeah, thank you, Simon Marlowe. And also the very friendly and helpful community. Yeah, could be the topic of another talk. So, what did we find that were not so good? Yeah, the disadvantages. Yeah, this very steep learning curve for imperative programmers. We are currently 1.5 developers in our company which know Haskell. Yeah, me and another colleague who's learning it, and there were a few others which were quite enthusiastic about it. But it's somewhere when they learn it and start to use it, then there is something like they hit the wall and then stop. And it's for me it's not clear why. So, but I'm working on it to get a little bit more inside our unit. Space leaks were interestingly less of a problem to us. I think it's because of the I/O-driven nature of the application, so the funcs don't have a chance to get built up. We had some performance problems in combination with the GUI. I think it's mainly because the GTK binding uses Haskell standard strings, which are just a list of characters. So, and the conversion to the C, low-level C string type, maybe and if you have lists with 40,000 parameters, can get slow. We are still on the green side. We decoupled the GUI from the processing model, and so that the performance doesn't impact the model itself. But that's one of the things. And also we had some problems with profiling. Not exactly sure what the problem was. I just wanted to know where we lose the speed. And then I ran into these problems, but because we were still on the green side, I didn't follow this further. And also what we found was the lack of series tracing, this file line and func macros. I think Leonard Augustin has done something on that. And also I got from the tutorials, I got also a lot of ideas what we can do now. And also a problem for us was that there is no for us usable CORBA implementation, because SCOS uses CORBA as the middleware internally, so it would be easier to connect systems. So I've already done some tests to use the foreign function interface to interface with the CORBA ops, and it went quite well. So now doing some kind of guerrilla tactic to get Haskell a little bit more in. And also DLR now starts to see that the features are much quicker implemented in the simulator than in the mission control system. So that's what starts a little thinking process. So, okay. Yeah, so in short, work done, it worked. We will use it in the future if we can. I blogged a little bit about the architecture of the application. You have the link, there's also a link to the company site and a link to the DLR homepage. There you can get further information of the missions if you like, and there are also some pretty space pictures there to download. Okay, so that's it from my side. Thank you for your attention.
First of all, thanks. And second, you said that imperative programmers tended to hit a wall, and you said you weren't sure why, but do you have any idea what particular constructs they hit a wall on?
Yeah, I think it's the very different mindset of Haskell. So you start to think differently, and I think I've also seen this in designs. If you architect an application, you think a lot in the programming languages you are used to. Yeah, and most of them are C++ programmers, TKTK, Python, whatever. So they think in this world. And if there comes something completely different, yeah, I know when I started Haskell, I had these knots in my brain. How can you do that? It should not work, yeah, but it works. Yeah, and I think it's a mindset problem.
And also, when you said imperative programmers tend to hit a wall, were you comparing them to anybody else? Were you comparing them to people learning Haskell as a first language on your site, or just compared to using the languages they were used to?
We don't have people which start learning Haskell from scratch, so can't really compare that. Most of them are old-time programmers, and yeah, I don't have data about this.
I have another question, if someone else has a question, I will let them go. So you said that you saw like between a 1.5 to 4 times productivity improvement. So first of all, that's a fairly big range. So if you were in the business of estimating that more precisely, what do you think you would look at based on your experience? And relatedly, you mentioned reading the Hudak paper about productivity in the beginning, and do you think line count is a good metric? And if not, what do you think is more important?
Yes, no, line count is not really a good metric. So, we had tons of discussions about metrics, suitable metrics in our company, and we still haven't found a really suitable solution. So, no.
Function point analysis.
Maybe, yeah. There's still some of my colleagues argue against it. So there are pros and cons. And for the 1.5 to 4, it's a big range because, of course, it was also a learning process for me. So I started to, for some things I was even slower, but I didn't count it for this tool because this was in the applications I built before. So to get into it, to learn it, and so on. So that's why the big range is. So it's still a work in progress.
Thank you. Anybody else?
Thank you very much for your time.